Imagine boarding a brand new airplane, feeling safe and secure, only for it to tragically crash within minutes. This nightmare became a reality twice with Boeing's new 737 MAX aircraft, just 5 months apart. These weren't isolated incidents, they shared chilling similarities that puzzled the world and grounded an entire fleet of planes. Today, we're going to break down the real reasons behind these devastating events, understand the complex engineering challenges involved, and see what lessons the aviation industry has learned. It's a story of innovation, unintended consequences, and the critical importance of safety in the skies. First, let's introduce our main character, the Boeing 737 MAX. The 737 is one of the most successful commercial aircraft families ever, continuously updated since the 1960s. The MAX was designed as Boeing's latest iteration, aiming for greater fuel efficiency to compete with rivals. To achieve this, it needed larger, more powerful engines. Think of it like upgrading your car engine for better mileage and performance. This seemingly straightforward upgrade, however, introduced a significant engineering challenge, one that ultimately set the stage for the tragedies to come. Understanding this core change is crucial to understanding the subsequent problems. Here's where things get tricky. The new, larger engines on the 737 MAX wouldn't fit under the wings of the existing 737 design without hitting the ground. So, Boeing's engineers had to mount them slightly further forward and higher up. This might sound like a small tweak, but it had a big impact on the plane's aerodynamics, how air flows around it. Specifically, under certain flight conditions, especially when the plane was flying slowly with its nose pointed up, these new engines caused the aircraft to pitch up even more aggressively than previous 737 models. This made the plane feel less stable to pilots and less like the 737s they were used to flying. To counteract this new pitch-up tendency and make the 737 MAX feel consistent with older 737 models for pilots, Boeing introduced a new automated system, the Maneuvering Characteristics Augmentation System, or MCAS. The idea was simple: if the plane sensed it was pitching up too much, MCAS would automatically push the nose down slightly to maintain stability. It was designed as a safety feature, a silent helper in the background, making the new plane fly just like the ones pilots had been flying for decades. But this helper had a critical flaw in its design that would turn it into a significant problem. Here's where the system went tragically wrong. MCAS relied on data from angle of attack, or AOA, sensors. These sensors measure the angle between the wing and the oncoming air, crucial for preventing stalls. The fatal flaw was that MCAS only used one of these sensors at a time. If that single sensor failed and sent incorrect data, for example, falsely indicating the plane's nose was too high, MCAS would activate automatically, repeatedly pushing the plane's nose down, even if it wasn't necessary. It would act like a stubborn autopilot, convinced it knew best, against the reality of the situation. Compounding this technical flaw was a critical lack of information for pilots. Boeing chose not to disclose the existence of MCAS in the flight manuals or pilot training for the 737 MAX. The assumption was that MCAS would only activate in rare, extreme circumstances and would feel transparent to the pilots, easily overridden if needed. So, when MCAS activated due to faulty sensor data, pilots faced an unprecedented emergency. They weren't trained to recognize the system's behavior, let alone how to effectively counter its powerful, repeated nose-down commands. They were flying blind against an unseen, malfunctioning automated system. On October 29, 2018, Lion Air Flight 610 took off from Jakarta, Indonesia. Shortly after departure, a faulty angle of attack sensor began feeding incorrect data to the MCAS system. The pilots fought a terrifying battle, repeatedly pulling the nose up as MCAS pushed it down, leading to a relentless struggle for control. Despite their valiant efforts, the plane ultimately plunged into the Java Sea, killing all 189 people on board. Investigators quickly focused on the plane's automated systems, but a full understanding of the MCAS issue was still emerging. Just 5 months later, on March 10, 2019, the unthinkable happened again. Ethiopian Airlines Flight 302 crashed minutes after taking off from Addis Ababa, Ethiopia, killing all 157 people on board. The flight data recorder revealed a chillingly similar pattern to the Lion Air disaster: another faulty angle of attack sensor, another struggle against the MCAS system repeatedly pushing the plane's nose down. 2 crashes, 2 brand new planes, and the same terrifying sequence of events. The immediate result was a global grounding of all 737 MAX aircraft, an unprecedented move in modern aviation history. How could a system with such a critical single point of failure be approved? Investigations revealed significant issues with the certification process. Due to increased pressure and a desire to expedite approval, much of the safety assessment for MCAS was delegated by the Federal Aviation Administration, or FAA, to Boeing itself. This self-certification model, combined with an underestimation of MCAS's potential power and a lack of proper communication within Boeing, allowed the flawed design to slip through. It highlighted systemic breakdowns in regulatory oversight and the urgent need for reform in how new aircraft are approved for flight. Boeing immediately began working on a critical software update for the 737 MAX. The revised MCAS software now uses input from both angle of attack sensors. If the sensors disagree by a significant margin, MCAS will not activate. Furthermore, MCAS will only activate once per event and with less aggressive nose-down input, and pilots can always override it using the control column. This fundamental redesign ensures redundancy and gives pilots ultimate control. Extensive testing and additional pilot training were also mandated before the aircraft was allowed to return to service, restoring some confidence in its safety. The tragic crashes of Lion Air 610 and Ethiopian Airlines 302 were a wake-up call for the entire aviation industry. They underscored the critical importance of robust safety design, transparent communication between manufacturers and operators, and rigorous, independent regulatory oversight. The focus on automation must always be balanced with ensuring human pilots retain ultimate control and are fully informed about all systems. While these events were devastating, they led to crucial changes that will hopefully prevent similar tragedies. It's a somber reminder that in aviation, every detail, every line of code, and every training manual has profound consequences.